Hi guys, welcome back. So today's lesson is on solving log equations or logarithmic equations. So just as a reminder, of course, what are logarithms used for? We use them to solve for unknown exponents. So we've seen a lot of that in the last lesson. We have two new properties. One of them we saw last time, that I can take the log of each side of an equation. As long as I do that to the entire quantity. Well, today we're going to add in a new one, which is that we're also allowed to exponentiate both sides. So this is kind of a weird one here. But exponentiating both sides is basically, if I had some expression here, 2x plus 1 equals 7. To exponentiate this, you could basically write each side as being 4 to the 2x plus 1 power. And 4 to the 7th. Like, we can turn this entire side into an exponent and pick a base of whatever base we want. This is called exponentiation. So just as a quick review of what you would have seen in our last lesson. So if you were solving this equation for our logarithms here, we could, in this case, take the log, and we'd want to use the base of our unknown exponent, so log base 5 of both sides. So we take the log of both sides. Okay, it would look something like that, log base 5 of both sides. Over here we could see that the base of 5 and the log base 5 basically cancel each other out. Okay, so our x plus 1 will drop out of there. And we get x plus 1 equals log base 5 of 7. Okay, last thing to do is get x by itself, so subtract your 1 over. And now we have an expression equal to x. Now remember that exponents, like our variable up here, could be positive, they can be negative, they can be any number, right? Any real number. So we don't necessarily have to check that our answer is valid, only that it's correct. So for instance, here is log base 5 of 7 minus 1. There's our approximate decimal value. And I went ahead and stored it as x. So let's check to see if this works. So we plug in 5 to the x plus 1. And if we did this correctly, it should give me back approximately 7, or very, very close to 7. And in fact, it is so close my calculator just said it's 7. So here we could say our answer or value for x is approximately 0.0291. Now let's take a look at a value, or an equation, I should say, that we'll be solving today. So here my unknown is inside of a logarithm. That's what makes this a logarithmic equation. And we have logs on both sides. So the property that we can use today is that we can exponentiate both sides. So we'd want to look is the base of our two logarithms here, which is base 2. And we're going to raise each side, like as a power, using 2 as our exponent. So essentially it looks like this. 2 to the log base 2 of x plus 1 equals 2 to the log base 2 of 4x minus 3. And just like before, these logarithms will cancel each other out. Or I should say the base of 2 and the logarithm of base 2 will cancel each other out. They are inverse operations, so we're canceling each other out here. So that would leave us with our next step, which was just what was inside of our parentheses here. X plus 1 has to equal 4x plus 3. So lastly, getting x by itself, so moving our x's to one side of the equation, my constants to the other, and dividing by 3, we should get 4/3. Okay, another part that's important to see with this type of problem is when I had log base 2 of something equals log base 2 of something, we could even assume in this case that these expressions are going to have to be equal for those logarithms to be equal. So we might have seen last year, depending on how this is presented to you, that if you had something like log base 2 of x equals log base 2 of 5, that for these two things to be equal, that x is going to have to equal 5. These values have to be equal to each other for those expressions to be equal. So it's also good to kind of visualize, if I get this one log equal to another log, the inside values are going to end up being equal, right? We can kind of skip to the step we got here. Okay, so really quick, a little bit of review here. So remember, for our definition of a log, so if I have a log base b of x, that the base has to be a non-negative value that's bigger than, that's not equal to 1. Can't have a base of 1, and it can't be 0 or negative. But the more important part here is that the inside value, the expression x, always has to be positive. So when we're checking our answers in this unit, we have to check that anytime I plug a value of x back in and evaluate it, that none of the insides of my logarithms become undefined, or that we go out of our domain. So as a reminder, the value of any expression inside of a logarithm must remain positive. All right, here's two examples where we're going to solve for x. So we'll talk about exponentiating each side. We'll also talk about where sometimes we can just set the values inside of each one directly equal. Okay, so our first one, number 1 here, we've got log base 3 of 2x equals log base 3 of 10. So we want to use the base given 3, and we can exponentiate each side. So think of it as 3 raised to the log base 3 power, and 3 raised to the log base 3 power, where our base of our exponent and our logarithm here will cancel each other out. And so we'd be left with the inside expression 2x equals 10. Okay. Now all we need to do is finish solving for x, and dividing by 2, we get 5. But remember that we need to check that anywhere I plug in this value of x, the insides of my logarithms remain positive. Okay, so if I were to substitute back in here, 2 times 5 is 10. That is a positive value, and of course it does make them equal. So yes, there is there's my only solution for that problem. Okay, again, it's also good to look at this though and say, hey, I have log base 3 of something equals log base 3 of something, right? Log base 3 of 2x equals log base 3 of 10. For these things to be directly equal, 2x is going to have to equal 10. So I can even kind of visualize getting straight to that step there as well. Okay, so we've got kind of two options that we're thinking about where we can apply both to number 2. The problem will just be a little more complex here. So this time, remember our natural log, that our hidden base here is base e, the natural number e, or Euler's number, however you want to say it. Okay, so again, we can exponentiate both sides, like e to the natural log, base e, same thing here. And then we can cancel out our natural log with base e and our base of e. And so we would get the expressions 2x squared plus 3x equals 5. Okay, and once again, because we had just one logarithm equal to one logarithm, you could visualize getting here by saying that expression is going to have to equal 5, right? And that's exactly what we got in this step. Okay, let's go ahead and finish solving here. Now I notice that we have a quadratic term, right? We also have a linear term and a constant. We've got a full quadratic to deal with here. So to solve for x, we're going to have to use our quadratic techniques. Subtract the 5 over and set it equal to 0. Maybe before quadratic formula, maybe this factors. And I think it does, looking at these numbers. So one way of kind of quick checking, especially when a is not 1, is you can imagine multiplying this over. 2 times negative 5 is negative 10. And then if the answer to this next question is yes, it's factorable. Are there factors of 10 that subtract to 3? Are there factors of 10 that subtract to 3? So factors of 10, yep, we have some that subtract to 3. And I don't care if that 3 is positive or negative. This is just like a yes or no. Is it factorable? And so our answer here is yes. It is factorable. So maybe we don't need to use full quadratic formula. We can kind of do our guess and check factoring method here. To get to 2x squared, we can do 2x and x. And to fill in my middle blanks here, they're going to be opposite signs. I think the bigger numbers needs to be multiplied by 2x. And probably the smaller number multiplied by x, or the negative number here. So I'm going to go with, let's go with 5, positive 5, and negative 1. That sounds better. All right, now that that's factored, those would be the correct terms to get us the correct middle of positive 3x and multiply to our negative 5x at the end. Okay, so now I want to be able to set each of these equal to 0. So using 0 product property, here you can imagine 2x plus 5 equals 0, or, that's a terrible x, So imagine 2x plus 5 equals 0, or x minus 1 equals 0. And setting each equal to 0, here you should get negative 5 halves. Subtract 5 and divide by 2. And here, adding 1 over, we get positive 1. Okay, but before we mark these as our solutions, again, any logarithm that has an x in it, or our variable, we need to check that if I plug in, it remains positive. So this one doesn't have any values of x. I need to be focused over here to check that these are valid solutions. So 2 times x squared plus 3 times x has to stay greater than 0. So if we plug in our two different solutions here, if I plug in 1, well, this is going to be a positive term, this is going to be a positive term, and adding them together will certainly stay greater than 0. So I'm good with 1. It's this negative 5 halves that we need to be a little bit wary about. So negative 5 halves, just to double check here. Squaring this, I get 25 fourths times 2. Here, multiplying these together, we get negative 15 halves. Multiplying by 2 here, you would get 50 fourths, which of course you could cross-reduce as well. Oops, not twelfths. I don't know where I got this 1 from. Ignore that. That's just a 2. And then, yeah, this is 25 halves if I reduced, and negative 15 halves would give me positive 10 halves, or 5. So yes, it does stay greater than 0, and we end up getting that when I plug it in, oh yeah, lo and behold, it does equal 5. Okay, so both of them were valid solutions this time. It's something that you always want to make sure you check. Sometimes both may be invalid and there's no solution, or maybe just one of them is invalid. But we do need to test all answers in any logarithm that has an x in it, that the overall expression remains positive. Okay, these next two, we're going to also need to employ combining or condensing our logarithms so that we get either one log on each side. I want to condense each side down to at least a single logarithm if possible. Okay, so on number 3 here, we need to use, in this case, the quotient property. We have two logarithms with subtraction between them. So there's no exponent rule to use here, or power property. So we can go straight to the quotient property, which remember is the top minus the bottom. So x would go on top of our fraction, x plus 3 on bottom. Okay, so here is combined. I have 1 log equals 1 log. Now we can exponentiate both sides. Remember, our hidden base here is e for the natural log. So we can exponentiate both sides to cancel out those logarithms, which leaves us with x over x plus 3 equals 6. Again, or we can think of this case as once I got 1 log equal 1 log, the inside values have to equal each other, right? So x over x plus 3 has to equal 6. So you could also skip to that step if you don't like thinking about exponentiating, but they will both get us here. Okay, now I have a rational function, and if it's just one fraction equals one fraction, we can actually cross multiply here. So if you remember cross multiplying, we will need to do some distributing. So cross multiply this 6 gives us 6x plus 18 equals x times 1, or x. So let's move our x's to one side of the equation. 18, that's supposed to be an x. Let's pretend, play pretend. Minus 5x equals negative 18. Divide away our negative 5. And we get x is 18 over negative 5. So this is a negative value. Well, it's the only solution I came up with, and I can tell right here, the only thing I'm doing with x in that expression is plugging it in. And I have a negative value there. Remember, I cannot have negative values. This ends up being an extraneous solution, and there is actually no solution to this problem. Okay, plugging in and checking it makes my logarithms undefined. There is no solution. If you were to graph this, you graph this side of the equation, and then you came back and graphed this side of the equation, and you tried to find where they intersected. Okay, they don't. That's why we end up with no solution. Okay, let's try our next one here. This time, again, I need to worry about that I have something over here that's not part of a single logarithm. Okay, so we have two choices here. We can either replace 2 with a logarithm that has a value of 2 in base 5. So maybe you could come up with that on your own. Let's see, 5 to the second power would be 25, log base 5 of 25. I could substitute in for 2. That is a logarithm that has a value of 2. Okay, that might be confusing and maybe not the most obvious for most of you. So let's say instead we move our logarithms to one side. So let's move the log base 5 of x minus 1 over here. Okay, so we move this to the other side. Now I have 2 equals log base 5 of 3x plus 4 minus log base 5 of x minus 1. And now we can use our properties of logs to combine these two into one logarithm. And again, it is the quotient rule, since we have subtraction. So top minus the bottom, 3x minus 4 goes on top, or plus 4, sorry. And x minus 1 is going to go on bottom. And then from here, now that I have just one log on each side, or a log equal to a number, this is where we can exponentiate both sides. So because the base of our logarithm is 5, we're going to use 5 as our base and exponentiate. Okay, so here 5 squared gives us 25. And over here, these cancel out. Equals 3x plus 4 over x minus 1. Once again, we get a rational function to solve here. Let's put this over 1 and cross multiply. So 1 times the quantity 3x plus 4 is just 3x plus 4. Don't forget to distribute if necessary, and with our 25, it is necessary. That gives me 25x minus 25. So now we need to put our x's on the same side, maybe subtract 3x over. So we get 22x, and add the 25 over, which gives us 29. Okay, so divide away the 22, and we get 29 20-seconds, which is a little bit of a pain to solve. But this does have a value bigger than 1, right? It's a top-heavy fraction. So I'm imagining checking in this first one, and if it's a number bigger than 1, minus 1, that stays positive. So I'm okay with it being positive there. And over here, hey, I'm multiplying it by 3. That just makes it a bigger positive number. And I'm adding 4. It definitely stays positive. So it passes all the checks of staying positive. It's not a domain restriction. The only thing I would need to do now is maybe test this value that it does make these two things equal. But suffice to say, it does. 29 20 seconds makes them equal. Okay, just to show you that they do end up being equal, I've stored that value as x. And let's plug it into this equation, and it will give me a true or false statement, whether this is true or false. And there we go. If that's my value of x, these two things are equal. True. Okay, 2 more examples to practice here. This would be a good time to pause, try out, say, example 5, and then check your answer in a second. Let's go ahead and pause the video now. This is very similar to our last example. Try number 5. All right, how did you do? So we got some extreme numbers in here because we ended up with 10 to the third. We got a fraction that gave us a value really close to 3.5, but just underneath. And if you checked that back in here, I used the one on the right, but really if you try both of them, it does fail both of them, but it only needs to fail one for us to throw that solution out. So 3.99 did not work. It made our logarithms undefined. We got a negative value after we plugged in. So no solution. Okay, if you're feeling confident, I would say pause the video and then try example 6. You do have to do a power rule in here as well, which we haven't gone over, but go ahead and give this a try. If you would like me to walk through it step by step, that's what I will be doing next. If you're done and you just want to check your answer, you can fast forward towards the end. Go ahead and pause now. Okay. For those of you guys that want me to walk you through this one, let's do it because we haven't done one that's just like this. Okay, for number 6, first thing again is we have multiple logs on one side that we need to use our properties to condense. And this time, it's the first time we've seen a multiplier outside. Remember, this is like our power rule where we get to bring this thing back in as an exponent. Now you could bring it in as a negative exponent, but I'm not going to do that to you because then you do have to remember more about negative exponents. But either way is technically fine. So we can bring this in as minus x squared, x to the second power there. Okay, equals log of 5, and everything else just drops down. Now, next, we need to use the quotient rule, once again, because we do have subtraction between them. So we're going to get log base 10 of 12x minus 4 over x squared equals log of 5. Okay, good. So this is now I have one log on each side. We can exponentiate both sides. So in this case, our hidden base here for the common log is base 10. So we can exponentiate both to the 10th power, cancel the log base 10 out with those, and we get the expressions 12x minus 4 over x squared equals 5. And again, we have a rational function here. Now, we didn't mention some of these before, but of course, the rational functions themselves do have some restrictions, like the denominator can't be 0 here. And in the previous problem, we could say that, of course, this can't equal 0. Now, that does go along with our restriction that this whole expression has to stay equal to 0, just like that, or sorry, greater than 0, just like that had to stay greater than 0. Okay, back to this problem, though. We can once again cross multiply, so 5 times x squared is 5x squared equals, and then 1 times 12x minus 4 is 12x minus 4. So I see we have a quadratic. Let's move everything over to one side. So subtract 12x and add 4. And then we can try factoring again. I think it is factorable, or you can try quadratic formula if you want to do the longer way around. Okay, but this does factor. I believe it's 5x and x. And I want to say we're looking with -2 and -2. That looks correct. That would give me negative 10x, negative 2x. Good. Negative 12x and positive 4 when we multiply. All right, setting each of these equal to 0 and solving, we should, of course, get positive 2 halves, add 2 over, divide by 5. And here, adding 2 over, we get positive 2. So this does give us two things that we would need to check. Okay, where they're both positive. So if I imagine coming back over here, in this logarithm, they would both stay positive, so that's good. I'm more worried about over here that when I subtract 4, 12 times 2, that's definitely, I mean, that's positive 24, minus 4 is positive. 2/5 maybe is a little bit of concern, just to show you that I think we're okay here. 12 times 2/5 minus 4 needs to stay greater than 0. So multiplying here, you get 24/5 minus 4. And this is some value just barely under 5, right? I mean, this is what, 4.8, which does stay positive. So it passes our validity check. It doesn't violate our domain here. And of course, I could check with the calculator just to make sure that these do make these two things equal. If we were to graph the left-hand side and graph the right-hand side, these intersect each other twice. And the two x values of those points of intersection are positive 0.4 and positive 2. So here you go as a quick visualization here at the end. Here is the left-hand side of our equation, log base 10 of 12x minus 4 minus 2 times log base 10 of x. That's this weird curvy blue graph here. And then the constant, log base 10 of 5, that decimal value is graphed here for y. And if we look for our points of intersection, we can see that there are 2, and our two x values are 2/5 or 0.4 and positive 2.